We had an instructor Q&A session about exam questions, mostly just going over past exam questions, but also answering some of the logistical questions about the exam. And here's the recording.
Yeah, good question. The question is, in this particular example, which is spring 2020 midterm 1, question 2, why is it that this return statement on line 5 returns a function instead of a value, like taking the absolute value of unit, which would give you 2? And the answer is that that is what a lambda expression always evaluates to. So whenever there's a lambda expression, it is creating a function. Now, the lambda expression starts with the word lambda, includes the colon, and then has some expression after the colon. That altogether is a lambda expression. What you see in the line above is actually more than just a lambda expression. Here, there's a lambda expression, lambda t park, but then it is part of a larger call expression. And that's what those extra set of parentheses with s in it are, is that saying not just create this lambda function, but call it. Whereas in the following line, line 5, it creates the lambda function, but doesn't call it. So you have to kind of look around at the rest of the line to figure out what happens to it. And the answer is that the result, this function, is returned. So that's why you would write it as the return value of the people frame is a function, a lambda function. This is its body. And the other important thing to remember is that this was created while we were in the people frame. So that means that the parent of this lambda function will be the people frame in which it was created, which I think in this case would be F1.
By the way, notice too that this lambda does not have a parameter. So usually we've been seeing lambda x, lambda t, lambda y. So that is the function that takes a parameter, and then after the colon is that's what it returns. This function just doesn't take any input, so it's fine. It simply returns the absolute value of unit. Unit is bound to what you see in people because of what John was just saying about the frame. Hey, John, there's a question on the chat room about the ID for the showing ID for the exam. Can you just say something briefly about that? Because I know there's been a lot of back and forth on that.
Yeah, sure. So any photo idea will do. We're going to ask you in the announcements period between 7 and 7:10 to just show your ID to the camera. If you don't have a camera running because you were excused from that or your camera's not working or whatever, then you could skip this part. But if your camera's working and you have an ID, then just show it to the camera and we will give you explicit directions about what to do. And I'll tell you what the directions are now. It's hold up your ID in front of the camera for 8 seconds. Now, any ID is fine. If it's got your photo and it's got your name, you can cover up other stuff. That would let us confirm that it's really you taking the exam. All right, let's take a look at this together. So the question was about, this is fall 2016 midterm 1, question 5. And yeah, this was probably the trickiest one on this exam. So like I always say, don't focus all your time on the tricky ones. But let's take a look together. And we'll try to focus on when to return a function versus something else. So an order 1 numeric function is a function that takes a number and returns a number. Okay. An order 2 numeric function is a function that takes a number and returns an order 1 numeric function. And likewise, an order n numeric function is a function that takes a number and returns an order n minus 1 numeric function. Okay, so if it's order n, then we're going to call it repeatedly n times, and eventually we'll get a number. The argument sequence of a nested call expression is the sequence of all arguments in all sub-expressions in the order that they appear. So f here is called repeatedly on 3, 4, 5, 6, 7. Okay. Multiadder, it takes a positive integer n and returns an order n numeric function that sums an argument sequence of length n. Okay, so I guess this will sometimes return a function that returns a number. And it will sometimes return a function that returns a function that returns a number. For example, if n is 2. But it will never return a number because it's forcing n to be greater than 0. And so we have to pass it at least one thing to sum up. Okay, so looks like there's not going to be a ton of code. If something is true, then we'll return some function. Otherwise, we'll return some other function. I think in either case, we need to return a function because, well, here's an example. If multiadder is called on 1, then we return a function that, when called on 5, just returns 5. So I think we could actually just handle this example on the first line and then see if we can work from there. If n is 1, then now it's very important to know how to say return a function that takes 5 and returns 5. The way you would write that is lambda. And then you have to pick some name. You could pick any name you want, although it will be a little awkward to pick n. It would actually work in this case, but let's avoid n because it's already used and pick something else. So we kind of have handled this simple case where if we're just adding one number together, then we just return it. The sum of one number is just one number. The more complicated case, I guess, is this one, where if n is 2, then we need to return a function that takes some number, and that returns a function which takes some other number. Here I've built something that kind of does what we want. It says when this is 2, then we want to take in 2 arguments. And in fact, if this is 4, then we want to take in at least 2 arguments. So that's how we got to this structure, is just to say, like, I need to be able to look at 2 things at once in order to add them. And I know if n is not 1, I'm going to have to take in at least 2 arguments in sequence. So that's how we got the lambda k, lambda j structure. If we were just passing in 5, 6, then we would have written that, and life would have been a little simpler, but we didn't write that. So now we have to think about what to do. It's all about the behavior. This is supposed to be a function which takes in k and j. And in the case that n equals 2, we really just want to add k and j together. And I think if we didn't have to worry about n greater than 2, we would be done. We'd just write add k and j together, and we're finished. The problem is with n equals 3. Now all of a sudden we have to handle more stuff later. So we have to figure out how to do that. One way to do that is to say that adding 5 and 6 and 7 together is the same as adding 11 and 7 together. That was kind of the insight in this problem that you'd have to discover in order to solve it. So you could make this 11, but then you'd still have to add all the other stuff. Now, what might that look like? Well, if we want to create a function that takes more arguments, then I think we would need to call multiadder. Instead of taking 5 and 6 and 7, now we want to take 11 and 7. So the first thing that you pass to multiadder is not the number that you want to add together. It is the number of arguments that the result will eventually take. And here, since we're moving from 5, 6, 7 to 11, 7, I guess we need to take fewer arguments. Yeah, we might be done with this question. So now we'll just check and see what happens. So if we pass in n equals 3 originally, then we end up in this case, we return a function that takes k and j, which would be 5 and 6. Those will eventually get passed in. So this will be 5 and 6. And what we'll return is a multiadder that takes a sequence of 2 arguments, where the first one is 11, which means it still needs to take one more argument. That one more argument would be 7. So when we pass in 11 and 7 as the kind of next version of k and j, then that will add 11 and 7 together to give us 18, which will be passed in as the argument to multiadder 1. Multiadder 1 will return a function that takes in 18 and returns 18, and so we'd end up with 18. So this isn't so much about programming mechanics as it is about understanding what these different components do. And yeah.
Yeah, came up in the chat room, John, as a number of people are asking, isn't this recursion? And the answer is it's a version of recursion because you're calling yourself from within the body.
Yeah, I mean, technically recursion is a function that calls itself. And here multiadder doesn't call itself. It just returns a function. So technically this isn't recursion, but it certainly has a kind of recursive idea behind it.
Recursion-like.
Everything we've talked about here is something that we've learned in this course, but at the same time, it is difficult to think about how you would express the return value from multiadder in terms of multiadder. It's one of the more complicated versions of what we've seen so far in terms of self-reference.
And to those asking on the chat, recursion is not part of this midterm. So you will not, we don't expect you we won't be talking about recursion for this exam. That's the next topic.
Yeah, but when we say that, like, people get confused about what recursion is, and that can be a problem. So you won't actually see that, where f calls itself. We'll talk about that later in the week. But you might see that. Now, the reason why we're not going to talk about this until later in the week is that crazy things can happen. When you call f here for this version, let me call these different things so that we're not so confused. When you call f here, f then calls f, which calls f, which calls f. You can get some like massive chain of computation just from one call. It's exciting, but it's not something we've really talked about much. Here, life's pretty simple. Like if you call g on 2, you really just get g back, and it's not like gonna run forever or do something complicated or create some tree of computation that's really hard to understand.
So notice the difference here, by the way, is the first one is recursive because you are calling the function. The second one is not recursive because you are not calling the function. You are simply returning the function, right? So there's none of that looping that John was just mentioning. So the second one, of course, is fair game. You can return the name of your function. It's fine, just returning some value. John,
so popping back to this, like multiadder only does work every time you call it. So you kind of know that since there's 1, 2, 3, 4 calls here, there's going to be 4 steps in the process. So in that sense, it doesn't have that recursive behavior of calling f, which calls f, which calls f, and you have to kind of trace all of that. But at the same time, it is kind of expressing multiadder in terms of itself, which that kind of thing does show up in self-reference once in a while, but this is a diabolical case.
John, somebody's asking in the chat about using IDLE Python Tutor versus CS61 Tutor for the exam. Can you maybe elucidate that a little bit?
You're not meant to be using IDLE, but because we'd like you to stay in the browser, just like makes things simpler on our end. But anything you want to do, you could just do in Tutor. So if you want to run examples, this is what I would recommend, is run them in this site, which is in scope, and you get there as tutor.cs618.org, or by going to cs618.org and clicking on the tutor button. So if you want to test things out, there's really no good reason why you wouldn't do it here. There's a separate interface, which is almost the same, called code.cs618.org. Some people like it more, but it does the same thing as Tutor. So just use the Tutor, and then you don't have to worry about it. But you are not allowed to use external applications like IDLE or an IDE or something like that. You do have to write code yourself.
2 questions about accessing prior exams during the exam.
You can read prior exams during the exam. You can read anything that's linked from cs618.org, and they are all linked from right here in the resources tab.
The next question was, can a student print out the PDF of the exam and then work on that on paper and then input their answers into the site at the end?
Yes, and in fact, whether you print the PDF is up to you, but I think the right way to approach this exam is to use the exam site and paper. And if you've printed out your notes, that's great. Okay. If you really want to know what Python's going to do and you can't remember, then it might make sense to open up Tutor and check. But most of this exam is just like use some paper, read the questions on the website, enter your answers on the website. That's the right way to take the exam. That's how it's designed. And all this other stuff that people are asking about actually isn't really going to help you at all. And so I would just ignore it. And yes, you're welcome to print out anything, including the PDF for the exam, anything you find on the website. If you want to print it in advance, you can. You don't need to go nuts and like print everything that's on the course website. I think that if you want to look it up during the exam, you could just look it up. But if you think that there are things that you definitely are going to reference, then go ahead and print them out. And yeah, I hope that answers your question. Let's take a look at this example, which is from Spring 2020, Midterm 1, question number 2. In order to answer your question, I think we'll just have to go through and do some of this. Okay, so people got defined for us. We define unit. We define t. Those are 1, 3, respectively. And we define park, which is a function. And it was defined in the global frame. So its parent is global. And then we call people on park. People is a global function, so it gets defined in the global frame. People's formal parameter is s. And s gets bound to the argument that was passed in. When you have an assignment statement like unit equals 2, it always affects the current frame. So we wouldn't be changing unit in the global frame. Here we're assigning park to the result of calling s on unit t and plus 1. So before we ever call s, we have to figure out what it is. Okay, it's the function park. And before we call it on anything, we have to look up what we're going to call it on. So we'll call it on unit, which is 2, and t, which is 3. So those are going to be the arguments to park. Park is a function in the global frame that has formal parameters t and park, and was called on, we did this work already, 2 and 3. And then we see what it does. It returns unit minus 2. So we look in here, where's the unit? Well, there's no unit here, so we look in the global frame because that's the parent. So we return 1 minus 2 is -1.
A follow-up question was about the value for unit that was passed into the park function.
Yeah, so one way to check your work is just to say this expression is in the body of people. Therefore, all of the names in this expression are going to be evaluated in an environment that starts with a people frame.
Another follow-up question was whether the parent of park was relevant to the frame for park. What parts were relevant and what parts didn't matter?
Yeah, good question. So the question is, doesn't this park parent G matter somehow? It doesn't matter for setting unit and t's values. Those are both evaluated before this frame is ever created and before the environment changes. Where this global parent does matter is when we look up the name unit, which is part of the park function. That unit will be evaluated in an environment that starts with a park frame, this park frame, in fact, and its parent being global really does matter. So when we look up unit here, we look first here, we don't find it, so we look in global as opposed to in F1. So to summarize, the parent mattered for this return value. It did not matter for the argument values. The argument values are always set before the function is ever called.
John, I'm looking at your battery and it's really low, which is making me nervous.
Oh, that is exciting, isn't it? Yeah, let me plug this in.
It's getting exciting.
Yeah, it's a good question. So there's some kind of general pattern for problems that involve memorizing things that have happened before. And we really only have 2 mechanisms for keeping track of stuff. We have assignment and we have function calls. Both of them assign names to values. So if you want to keep track of stuff that's happened before, like you want to sum things or whatever. And let's say I want to sum 3 things. Well, I could sum things 3 and 4, and then save that in a name using an assignment statement. And then I could sum things A and 5, and I will have really summed 3, 4, and 5 all together. So assignment does this. Calling a function is very similar to assignment. So I'm sort of making this up as I go, but well, okay. We could have done everything with makeadder. Because adder is exactly the kind of function which has a memory. Any function that's defined within another function has its code, but also has access to all the values for its parent function, and therefore any value of adder will remember the x and be waiting for only the y. So in this sense, we can make adder on 3. When we call it on 4, we've now added 3 and 4 together, but I could get ready to add that to something else. And then when I call B on 5, I've added 3 and 4 and 5 all together. So I'd say, like, well, let's make sure this actually works. Some things should return 3 plus 4 plus 5 is 12. And this big makeadder expression, I would expect to eventually return us 12 as well. There's the 12. So I've kind of given you 2 ways to keep track of what's going on. You could use an assignment statement, or you could pass the result of some computation in as an argument to a function which returns another function. Therefore, this inner function has as its memory or its context, or in fact in its environment, the thing you wanted to store, the x. If you would like to use 2 one-sided sheets of paper instead of 1 two-sided sheets of paper, that is fine, and you don't need to show it to us. Okay, so the question is there an example of currying that we could go over? This pattern of take 2 arguments and then do something, but instead of taking them all at once, you take them in sequence, so that the real work is the same, but the structure is different, because this one takes one and then the other, and this one takes them both at the same time, is a general pattern. This could be about anything, not just adding, but subtracting or multiplying or something more complicated. So the whole idea of currying is just to say, I don't want to say what this is in advance. I want to leave it blank. And how do you leave it blank? Well, you give it a name, like F. And then when it comes time to do the work, you call it F. Now, it doesn't really make sense to call this adder anymore, because we don't know that F is about adding anymore. It could be anything. So maybe we'll call it doer, and this, does something. I don't know. You can call it anything you want.
A follow-up question was, what's the point of currying?
It's a good question. So functionally, there's no difference, right? These things are all going to compute the same thing. It's just the mechanism for it is a little bit different. So the benefit of currying is you're essentially, in some ways, partially evaluating the function. Yeah. So every part of the curried function takes one parameter. So you're sort of building up this expression. And there's a time, for example, let's say I have a function of multiple parameters. Maybe I want to evaluate the first 3 parameters and then only change the 4th one. So the benefit then is I can create a function that is in the first three parameters and then applied to a variety of different fourth parameters without evaluating the whole thing over and over and over again. So it's really not a functionality issue, right? They all do the same thing. It's just the mechanism to get there.
Yeah, exactly right. And like, let's say you've already written a bunch of functions that all take 2 arguments, and they do all the work that you want to do. You don't want to have to go through and rewrite them all as make adders and make subs and whatever. You just want to call curry on each one, and then you're done. So it's basically just like breaking apart the 2 different pieces of make adder. One is that it adds, and the other is that it takes 2 arguments. Curry 2 just says, hey, here's the part about taking 2 arguments in sequence, and let F worry about what is actually going to happen at the end of the day. Oh, this looks an awful lot like the multi-adder problem, but let's work on it together. So the question is about spring 2020 midterm 1, question number 4, which, how's it work? You pick a number of functions you're going to compose together, like 3. Then you say what all those functions are. Like I want to abs the result of adding 1 to the result of adding 1 to something. And that makes a function which does these 3 things in sequence. So it takes in an argument, it adds 1 to it, it adds 1 to it, and then it takes the absolute value. So the reason we got 2 here is that we had -4, added 1 to -3, added 1 to -2, took the absolute value, we got 2. That's what this does. Let's look at the case where we're only composing 1 function together. If that's the case, then I think we want to return that function. So compose 1 abs, I think, is equivalent to just abs. So we're going to get in some new function, and we'll just return that. So if we passed in 1 for n, and then we passed in abs for f, we'd get a function that takes the absolute value of things. If we pass in -4 to that, then we get the absolute value of -4 is 4. Okay, let's take a look at this. What happens when n is not 1? Well, then we're going to take in some f, and we're going to take in some g, and we're going to at some point call f of g on something. But I'm not sure we know in advance what we're calling f of g on. So let's give it a name. Well, this is certainly part of it. Let's not worry about the template for now and just think about what happens. So now we have a function that, so our goal here, if we, for example, had n equal 2, would be to return a function that calls g on x and then f on x, and we'd be done. If compose was called on 3 things, and now we've taken in abs as f and add 1 as g, we still need to take this function and compose it with whatever comes next. So we started with 3 functions. Now we've kind of taken the first 2 and put them together. We still need room for the other one, which I think we could get by calling compose on n-1. Here we can now take in 2 functions. And it seems like the first one should probably be that. And then what would come next is like whatever this gets called on later. So I think to fit this into the template, we could get rid of the parentheses that are already provided to us. Except apparently it's impossible to edit something you've already written in Zoom, but you kind of get the idea. So let me just leave it at that, is that you'd not have to write these parentheses, but instead you could just have them already appear there.
By the way, notice this looks a lot like the previous example with the adder. Yeah.
It is basically the same question.
Yeah.
Anytime you see function that takes n and n is a number, you better make sure that if you're calling it later, you call it on a number. And you should think hard about what this returns. This returns a function that takes a function in this case. So you better call that on a function. So it's, I wouldn't generalize and say like, oh, you're always going to call this on n-1, or you're always going to call it on a function, or you're always going to return a function or something like that. Really the trick is to focus on, given the pieces that are already provided to you, which in this case are compose and call and on, make sure that if you use those, you use them on the appropriate arguments, and that you use the return values of those in an appropriate way.
Right. There's still some confusion about recursion versus returning a function. So let me just clarify. Recursion is when you call yourself from within the function, which is different than returning the name of the function. Yeah. So recursion is not on the exam. We'll be doing that, I guess, this week and next week. But returning, as you've seen in these two examples, is fair game. I want to emphasize something John also said is don't get bogged down in the hardest problems. The ones we've been answering today, I think probably John maybe agreed with you, are some of the harder ones. You should obviously want to do those as well as you can, but don't get too bogged down on those when you're doing the exam. Do the ones you can do and then worry about these later.
Yeah,
Okay.
the students who tend to get A's in this course are the ones who skip multi-adder and just make sure they get the rest of it right. So that's my general advice. If you really want an A+, I guess you got to learn how to solve that one too.
All right. One logistic question about uploading the recording. No, it doesn't have to be recorded before the exam is up. That would be unreasonable. So just when the exam is over, just go ahead and upload it.
Yeah, and if it takes a long time to process, you can go to bed and upload it in the morning. That's fine. I'm afraid we'll be done for the day, but it was a pleasure talking to you all. And good luck. And you know, take it easy. Work on the stuff that you know well. Make sure that you answer those questions right. And if you see something you don't know, it's okay. You'll still do fine on the exam. See you, folks.